welcome you all to the lecture on Phasor measurement unit PMU placements under smart grids basic to advanced technologies. In this topic today, we will try to understand the role of PMU, that is why Phasor measurement unit is important in the field of smart grid, because PMUs are being used at both transmission level as well as at distribution levels. So, the transmission level actually India has really gone ahead at global platforms where maximum number of PMUs are in place. However, in the distribution system we are not so advanced, but across the globe the distribution system technology need to progress, and few distribution networks started accommodating or implementing PMUs where actually different variables and parameters can be obtained, and accordingly necessary proactive control mechanism algorithms can be carried out. Now, let us see what are the topics we will be covering today. First introduction, we will see the background, and then purpose of optimal PMU placements. You see, the very important part of PMU here is the cost. If you wish, you can put PMU at each and every bus and measure all the variables, that is wonderful, okay. But if it is a 33 bus system, then if you put 33 PMUs, then the cost will significantly increase, and hence we try to understand what are those important nodal points where those low voltage PMUs can be installed, such that the overall system measurement or the data of the overall complete system can be received at the control center in an optimal way, and hence the optimal placement of PMU become an important. So, we will also look into those algorithms in the later due course of time. So, it is basically optimization tool where you run a DCOPF and the PMU optimal locations can be extracted. And then once you understand the optimal PMU placement model, then we have to go for problem formulation, and then probably we will move to next step of experimental results, and then we will also compare if there would be some classical or meta heuristic techniques for optimization for identification of PMU locations, and at the end we will talk about few case studies on IEEE transmission systems for PMU placements. Now, any distribution system today is not free from, most of them are having bit of renewable energy into it. If you look into our campus, we have almost 2.8 megawatt of renewable, and the peak is close to 8 megawatt. So, to me it is almost 30 to 35% of energy that are available to us at IIT Roorkee campus is due to renewable. And the same story across the country, especially the academic rooftop solar arrangements. But even if you go for a conventional distribution system with the provision of independent residences also can have access to renewable energy. So, the time will come where you will see at least 20 to 30% of renewable energy in any distribution system, they are from renewable sources. And once that is there, then there is a huge risk, the uncertainty is really keep on increasing, and both end generation as well as demand, they are keep on oscillating, because there is no clarity how much energy is available to me at next couple of minutes and how my consumers are going to behave. And hence it is important for me to monitor and control the system at given challenging time or intermittent generations or load variations. So, to do or to balance the load and generation, we need to carry out real time data analysis. So, real time information from measurement devices connected in the network is required for state estimation and other analysis. Okay. So, let us say if there is a couple of buses, okay, or n number of buses in a distribution system or probably any transmission system, where you can estimate the state of each and every node through proper measurement, but how we can do it with less investment with minimum PMUs, you like to estimate the state of the complete network become a challenge. So, most popular measuring device is Phasor measurement unit, popularly known as PMUs, and the purpose of optimal PMU placement that is PMU installation is limited by economic and infrastructure constraints. So, during my introduction I have very clearly mentioned, because of infrastructure challenges as well as the cost effectiveness, we cannot put PMUs at each and every place where the measurement is required or the data is important. However, we need to optimize that what are those minimum locations where PMU can be placed, so that the complete state estimation can be carried out. Now, the critical buses, critical generator buses, tie line buses are prioritized for those close monitoring, especially in transmission network. Whenever there is a tie line, we need to measure those. Similarly, two microgrids, they can be connected through a tie line, and hence those two nodes are important to me. Now, PMUs are costly. Optimal bus location are need to be found to reduce overall PMU installation cost. Now, when you talk about optimal PMU placement model, what we do is, first of all we need to have all the network data, that is your system data. Now, what is happening, let us say I do have a a distribution system, and similarly I can have one more distribution system, all right. So, this is one distribution system, this is another distribution system, and they two can be connected, all right. So, this is one of my microgrid, this is another microgrid, and this is a cluster of microgrids and become an overall system. So, we need to identify how do I follow those networks and the kind of amount of energy flow needed from one system to other, similar to a transmission network as well as within the system. And once you have the complete network data, probably for a one microgrid or multiple microgrids, and the base case DCOPF, you can run, and then you can obtain the true results, and then probably from the network data we can obtain what is PMU cost minimization algorithms, and then you can run your state estimation constraints, observability constraint, and finally you come out with your optimal locations. So, what exactly needed here is that, subject to state estimation constraints as well as observability constraint, we can run an optimal algorithm to minimize the PMU cost and determine the optimal locations of PMU. Reiterate, for example, if you have a n bus system, we have to put PMU at 10% of those n buses. So, if it is a 100 bus system, you can put PMU, let us say 8 to 10 buses as minimum as possible, but imagine you are ready to spend money up to 10 PMU. So, how to identify those 10 locations out of a 100 bus system is important. Now, we have done bit of optimization in the past. So, I am just presenting you. So, linearized OPF, that is DCOPF based problem formulation, and this is what the operating cost for me, the cost that need to be minimized, and these are the power balance equations, bit of constraints and flow limits for lines as well as power generation constraints. Each and every generator must have its minimum and maximum generation limit. Each and every distribution and transmission line must have its minimum and maximum MVA limits, and the power balance, the load must be equal to my generation. Now, the objective function, if you consider PMU, is my cost variable. So, I can say if there are xi locations, we are putting PMUs, and each PMU cost is going to be CPMU. So, then xi multiplied by CPMU will give me the total cost, and that need to be minimized. So, initially we are not deciding how many number of PMUs, but we are saying it could be 0 to n, and then the optimization algorithm will tell you what are those important locations you can go for installation of PMUs. And then having those state estimation constraints and as well as observability constraints, you can identify. So, we have tried with two systems. One is IEEE 14 bus system. As you could see, there are 1, 2, 3, 4, 5 uh, generators, synchronous condenser 2, and then you have actually a 30 bus system, IEEE 30 bus system, and both are transmission systems. And it has been identified that the optimal location of PMUs are found to be 2679 in case of 14 bus system, and it is going to be 2, 4, 6, 10, 11, 12, 18, 23, 26, 29 is considered to be the locations for the PMUs in a 30 bus system. So, instead of placing 30 PMUs, now we restricted ourselves to actually 10 of them, and instead of 14 we restricted ourselves to 4 of them based on the previous algorithm which has been presented before you. Now, let us understand about bit of experimental results. So, absolute error between DC OPF results and state estimation measurement for the buses, that is voltage angle and line power flow. So, what we have done, actually we have carried out DC OPF, it will give me the voltage angle at each and every bus, and using the state estimation also I can calculate the same parameters, and then we can understand the absolute errors for each system. And as you could see, the absolute error is as low as 2 into 10 to the power minus 3 range, which is the maximum error that you could see, the absolute error, and these are the bus numbers. So, each and every bus the DC OPF and the state estimation results have been compared. Now, this is my absolute error, as you could see, and so these are the bus numbers again 0 to 20, and as you could see the errors and how they are keep on varying. The same thing has been performed for IEEE 30 absolute error calculations. As you could see, the error is as low as 6 into 10 to the power minus 4. So, it seems to that with proper installation of PMUs, one can perhaps measure all the variables starting from currents and voltage and phases at each and every bus with both state estimation algorithms as well as your OPF algorithms, and those are comparable, means identifying the minimum number of PMUs that can perform as good as a complete measurement of the whole network. Now, when you go for classical optimization technique, there are a bit of challenges. The first one is binary linear programming, because this PMU sometime it is there, sometime it is not there. So, you to have actually yes or no, similar to capacitor placement algorithms. So, it will have many zeros and ones. So, the binary linear programming model is suitable for PMU placements used to solve a system of linear equalities or inequalities in binary unknowns. Mixed integer linear programming, at least one decision is not an integer. Nonlinear programming, either the objective function is nonlinear or one or more constraints are nonlinear. Now, we can move to graph theory methods, graph theory based study of relationship in terms of nodes and vertices, and is used to model pairwise relation between objects. So, I think these are different type of classical optimization techniques one can use to identify the PMU locations, and there are also meta heuristic techniques are being frequently used by different researchers. Talk about genetic algorithms, particle swarm optimization, tree search and topology methods. So, these are different algorithms are being used. So, I am not really, and all of you may be aware bit of those applications, but just to repeat again. So, the genetic algorithm, which is random search algorithms, and based on offspring and springs fitness survivals. Particle swarm optimization PSO, which is a very popular based search in which particles fly around in a multidimensional search space, changing and adjusting its position according to its and neighbors best experiences. So, probably those algorithms are also popular in identifying PMU locations. So, but though my preference will be always classical optimization techniques, but being a researcher or a learner, you can also experiment those techniques for identifying PMU locations in a large distribution or transmission network. And tree search and topology method is also spanning trees of the power system graph is used to find the optimal locations of PMUs based on a desired depth of unobservability. Now, there are a bit of merits and limitations, as you could see in each method actually. So, GA, genetic algorithm, binary search, integer programming, BPSO, and tree search and topology. So, the merits are actually, they are robust, adaptability, immunity. GA provides optimal solutions, but the GA has long execution time, and binary search mechanism, which talks about exhaustive search, deals well with conventional measurements, but it is quite time consuming and not tested for a very large IEEE system. Now, integer programming, which is computationally fast and adaptable, and constraints are non-linear. So, I think those who are doing classical research, my strong suggestion would be, please focus on classical techniques, and perhaps you can compare those results with non-classical techniques, but at least one classical technique is must to understand and appreciate how the algorithm is performing, or you can understand better about the insights of the situation, why those locations is A not B will be very clearly observed if you experiment on classical techniques. Now, BPSO is provide optimal solution, however, the computational time and contingencies are ignored, and tree search and topology, where it is simple logic for PMU placement and it is suitable for power system already equipped with few observable islands and non optimal results. So, for specific application, the tree search technology is also equally meritorious. Now, if you get into the number of PMUs for IEEE test systems, the lowest minimum number of PMUs to enable complete observability. So, please try to understand, if you have a n bus system, so to have complete observability of all those n buses, how many minimum PMUs are required to experience that. So, the minimum numbers placed PMUs in IEEE transmission test system is used the basis for algorithms comparison. So, we have considered IEEE 14 bus, 30 bus, 39 bus, 57 bus and 118 bus systems, and we found that we need 3 PMUs and 7 PMUs, 8 PMUs, 11 PMUs and 28 PMUs respectively. So, almost if you see, like with 10 to 25% installation of PMUs, we can experience complete observability. Now, it is a detailed comparison. We have many methods such as PSO, dual search, integer programming, search tree, genetic algorithm, taboo search, immunity GA, contingency constraint, binary search, generalized integer linear programming. So, we applied all the methods and then found for IEEE 14 bus system to experience complete observability, I think you need 3 throughout any algorithms. However, in 30 bus system it is 7, in 39 it is keep on varying 10, 8, 8 and so and so. For 57 it is going to be 11 to 12 and 13, and 118 bus system it varies from 28 to 29. So, this table perhaps actually you can find this reference, which is very important, 2011, the article published by Will Edwards Chowdhury and SP Chowdhury in 2011. They have done a wonderful piece of work where they have compared most of these algorithms, and for each bus system they have identified the minimum PMUs required, and that can help all the researchers and learners to understand which algorithm is the best among all, So, there is no concrete outcome, but as a whole we can clearly see from this representation which method need to be appreciated or considered. So, to me very blindly I could see that this contingency constraint algorithm seems to be one of the best, because it is giving me solution everywhere and this is the minimum throughout. So, contingency constraint algorithm or method for PMU placement in IEEE 30 bus system or 14 or 39, 57, 118 seems to be the brilliant idea. But probably if you increase the number of buses, then it is not a generalized guarantee, but almost I can say the classical techniques such as contingency constraint algorithms or method is best suited. So, these are 2 important references. So, first one is a one reference which is published in a conference. The second one is a very important reference, please go through it carefully. So, I think this will give an idea how to identify locations for PMU placement, and probably maybe you can explore more strategy for PMU placement. So, thank you once again for patient listening. Thank you.